All right, so just to have a quick recap, we were discussing prefix-free variable length codes, and we've seen four compression schemes so far. Firstly, the Shannon code, which achieves an expected length between h of x and h of x plus 1 bits. The Shannon-Fano-Elias code, which achieves an expected length between h of x plus 1 bits and h of x plus 2 bits. The Huffman code, which also achieves expected length between h of x and h of x plus 1 bits. But the Huffman code is known to be optimal in the sense that it achieves the minimum expected length over all possible prefix-free codes. Then we saw that if we did symbol-wise encoding using either Shannon or Huffman or Shannon-Fano-Elias codes, then the expected length would would grow as n times h of x plus n times a constant, right? So the difference between the expected length and the entropy would grow linearly in n, and that is something that we desperately wanted to avoid. We want to achieve a smaller expected length. So what we could do is do block-wise encoding using say Huffman codes, but we saw that that is not practically feasible because the complexity of constructing the Huffman tree grows exponentially in the alphabet size. So so the Huffman code, the complexity of designing a Huffman code would grow as size of at least as cardinality of x raised to the n for blocks of length n. Right? So in order to solve this problem, I introduced the arithmetic coding scheme. This is basically an extension of Shannon-Fano-Elias codes. It is essentially it is Shannon-Fano-Elias codes, but we have a nice recursive formula to compute f bar of x and p of x. Uh, the recursive formula for so the way we compute f bar of x is that we use this g of xn. Recall g of xn is summation overall an strictly less than xn p of an. Right? So this is our g of xn, and g of xn can be computed using this recursive formula. So g of x superscript n is g of x superscript n minus 1 plus p x superscript n minus 1 times g of x subscript n. Right? So the complexity of computing uh, g of xn is basically just linear in it. So even if we have large block sizes, we can use this formula and essentially construct the arithmetic code for any n length sequence. And since this is basically a Shannon-Fano-Elias code, the expected length that the arithmetic code can achieve would be less than or equal to h of xn plus 2 bits, but greater than h of xn plus 1 bit. Right? So this is a great scheme, and it is widely used in practice. Now, compressors don't use only the arithmetic code in like practical algorithms such as 7-zip or gzip. They don't use only arithmetic coding. They use something called Lempel-Ziv encoding, which we'll see in maybe the next in the next few classes. So they use the this scheme called Lempel-Ziv encoding, and then along with Lempel-Ziv encoding, they also use the arithmetic code to only encode certain parts of the file. Right? Because as we know that the arithmetic code is close to optimal for IID sequences, so it achieves n times h of x plus 2. So I should perhaps make this as n times h of x plus 2. Okay, so any questions regarding what was covered in the last class? Okay, so in this class we'll take a short detour. So we were discussing different algorithms, but maybe we'll take a step back and cover certain aspects that was left over in the previous classes, or something that we didn't touch upon. Okay. So what happens in practice? In practice, we don't really know the distribution, right? Even if we assume that the source is IID, we have xn, which we compress to get ck, and then we decompress to get back xn. And so far, we assume that the distribution px is known both to the encoder and the decoder. Right? So even if xn is IID px, Uh, now, there's no way to really know px. No one gives you px in practice. So what I had earlier mentioned is that what you can do is you can first estimate px by just counting the empirical frequency of various letters and use that as a proxy for px. This px can be stored as a header in the compressed file, so that the decoder also gets to know what you're using. Now, although one can do that, the estimate of uh, yes, please, any question?
Sir, whatever codes we have designed, Huffman, Shannon, and Shannon Fano alias code,
Yes.
are these valid only for IID sources or for any type of sources?
So you can use these codes for any type of source, but the rate that they can achieve. So all of these, so we've seen so far. Go back. Okay. Yeah. So these are valid for any kind of source, but for example, the expected length achieved by the Huffman code, as we know, is between n times h of x and n times h. So if you do symbol-wise encoding, then the best that you can achieve is n times h of x plus 1 bits, right? Similarly, the expected length achieved by the Shannon code would be between n h of x plus 2 bits and, sorry, the Shannon code would still be n h of x and n h of x plus 1 bits, right? So if we do symbol-wise encoding, the best that you can hope for is to get to roughly n h of x bits. And this can be achieved for any, so as long as the source is stationary and ergodic, you can achieve this particular rate. But for a stationary and ergodic source, this is not the best possible rate that a compressor can achieve, because as we've seen, the optimal rate of compression for a stationary and ergodic source, uh, the optimal rate is the entropy rate, which is limit n tending to infinity h of xn divided by n. and in general, this is going to be strictly less than h of x. So if it is an IID sequence, then the optimal rate of compression would be equal to the entropy. But for a source with memory, this is going to be strictly less than entropy. It's equal to the entropy rate, which is strictly less than the entropy. However, any form of symbol-wise encoding, even arithmetic codes for that matter, cannot achieve any rate better than the entropy. Okay, so you can do, of course, you can do block-wise encoding of using say the Shannon-Fano alias code or the Shannon code or the Huffman code and get a rate better than h of x. But then if you do symbol-wise encoding, then this is the best that you can hope for. If you use arithmetic codes, then you cannot do any better than h of x. But in general, if the source has memory, then the rate that you can achieve is strictly less than this. However, you can, as I mentioned, just to repeat, you can always use the Shannon code or the Huffman code or arithmetic codes for any kind of source sequence. It will still give you some rate of compression. Right? Yeah, so for a non-IID sequence, h of xn is not equal to n times h of x. It will be strictly less than n times h of x. Right? Then that just follows uh, by the fact that conditioning reduces the entropy of a random variable. So, for example, if you take a first order Markov source, then h of xn is h of x1 plus summation I going from 2 to n h of xi given xi minus 1. Right, this is easy to see. And if it's a first order Markov, it's a time homogeneous Markov chain, then this is h of x1 plus n minus 1 times h of x2 given x1, right? So the entropy rate h of xn divided by n in the limit as n tends to infinity is the limit as n tends to infinity of h of x1 by n plus n minus 1 by n times h of x2 given x1. So this is basically h of x2 given x1, which is strictly less than h of x2. Right? Sorry, the condition for LH and LS won't be what I wrote here. So LH and LS still achieve this particular rate, right? But but the best possible rate that you can achieve if you didn't use Huffman or Shannon codes, if you use the best possible code which minimizes the rate, then the rate that you can achieve would be h of x2 given x1. But symbol-wise encoding would get you only n times. So for example, the arithmetic code would get you only n times h of x2 plus 2 bits, which is larger than h of x2 given x1. Right? So for
Sir,
a state, yes, please.
so in the expression of ls and lh, you
Yes.
wrote, sir, n times h of x, sir, but it will be only the case when the sequence is IID. Otherwise, instead of n times h of x, h of x power n means the entropy of
No,
the
no,
whole
no, no, no.
sequence.
No, 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 no. So if you do symbol-wise encoding using Shannon codes, then the rate that you can so the expected length is n times h of x, right? Uh, it does not achieve h of xn. It achieves n times h of x. This is what is
So how's
achieved
the case?
using Huffman codes, right?
So, but generally, the lower bound is the entropy, sir. So,
The lower
how
bound, yes. So
so
the
how's the
entropy is less than this, right? So h of xn is in general less than or equal to n times h of x, but symbol-wise encoding. So if you do symbol-wise encoding of the Shannon code, I mean using Huffman codes, then what do you get? So the expected length k of xn, if you do symbol-wise encoding, is the expected summation I going from 1 through n k of xi, right? So if you do symbol-wise encoding, so this will always be equal to n times expected value of k of x, right? No matter what the distribution of the source is, whether it is IID or not, if you do symbol-wise encoding, then this is always the expected length that you get,
okay, sir.
right? For and at least let's say for a Huffman code, this is less than or equal to n times. So expected value of k of x is always h of x between h of x and h of x plus 1 and is greater than or equal to n times h of x. So all of these codes are valid for sources with memory, but in general they're always suboptimal for sources with memory. So all of these work well only for IID sources, but you can still use them for sources with memory. But they will give you a higher expected length than the optimal expected length which is possible. So all the compression algorithms that we've seen so far are optimal only for IID sources.
So it is not possible to achieve nh of x or nh of x plus 1 if we use memory sources with memory. These bounds.
So if you have a source with memory, then in principle it is possible to achieve a rate less than n times h of x. Right? The optimal rate of compression is strictly less than n times h of x. So the schemes that I've described so far will let you get to n times h of x, but in fact it should be possible if you designed a better algorithm, it should be possible to at least get to n times h of x2 given x1 or close to n times h of x2 given x1, which is strictly less than n times h of x. So so this is achievable using arithmetic codes, but this is theoretically achievable for first order Markov sources. Is that clear?
Yes, sir.
Okay. Okay. So any other questions? Okay. So as I mentioned, we've assumed that the exact probability distribution is given to you, but in practice that is not the case. All you have is an estimate of the true probability distribution, right? So if I call the estimate, let's say q of x, this is my estimate of p of x. This is not exactly equal to p of x, but is in some sense close to p of x. Right? So if you used q of x instead of p of x for encoding, then you can't really achieve entropy. There is a penalty that you need to pay. So the expected length that you achieve if you used q of x for encoding instead of p of x, the expected length that you would achieve would be larger than what you would get if you knew p of x exactly. Okay, so suppose we have x which is actually distributed according to p of x, but we don't know p of x. Okay, and maybe we only have an estimate q of x which we use for encoding. Let us say that we use the Shannon code, the Shannon code for encoding, but then we design the Shannon code according to q, not to p, because we don't really know what p is, right? So corresponding to symbol x, we would choose the length of the code word to be ceil of log 1 over q of x, right? So this would be the length of the code word corresponding to symbol x. But what is the expected length equal to? The expected length. So what is this equal to? So remember that p of x is the true distribution and q is your estimate. Yes?
Q of x into K of x or summation.
So, sorry, summation? Oh, what is inside the summation?
Summation Q of x into K of x.
Are you sure? Remember the true distribution is p of x, right?
So, but we don't know what is P of x. So, when we calculate expected one, then we
It's
obviously
it's
calculate using Q of x.
it's not calculation, right? You're not estimating the expectation. So what we're talking about is in reality, right? So suppose you use q of x to encode, but you actually have a source sequence which is distributed according to p of x, right? So x is distributed according to p, but then you encode using q. Yeah, so it's summation p of x times k of x, which is basically p of x c log 1 over q of x. Okay, so this is less than or equal to summation over all x p of x log 1 over q of x, or let's say this is greater than or equal to p of x log 1 over q of x, right? Because ceil of log 1 over q of x is greater than or equal to log 1 over q of x. Now let me multiply and divide this term by p of x. right? So, so can someone tell me what this simplifies to? If I split the term within the log,
KL divergence.
right? So it is d pq plus h of p, right? So it is equal to the entropy, the true entropy of the source, uh, plus the KL divergence, right? So what can you say about this? So this is the expected length that you can achieve. Right? So expected length k of x is greater than or equal to h of p plus dpq. So is this going to be greater than h of p or less than h of p, or can you say anything about it? So if it is greater, why is it greater?
Because entropy and KL divergence always.
Uh, Sorry, I didn't hear the last part of what you said.
Entropy and KL divergence are non-negative.
Yeah, so they're non-negative. In fact, they're always positive, right? So there is zero only. So h of p is zero only if p is sort of the trivial distribution. It's deterministic, and dpq is always greater than zero unless p and q are equal for all x. So this is, so as long as q is different from p, this is strictly greater than h of p. Right? So this is basically the penalty that you have to pay if you design your code according to Q, if when the true distribution is actually P. All right. Any questions? So this idea is also useful in practice in the following sense. So for example, even if, let's say that even if the source knew P, okay, uh, so even if the encoder knows P, okay, or it estimates P with a high degree of accuracy, you need to, after all, store P as the header, right? And and ultimately the number of, so you don't want the header to take too many bits of space, right? And after all, P is really a real number, right? So it's a bunch of real numbers. So if you want to represent P with a high degree of accuracy, then the size of the header blows up. So what you do is, instead of storing P exactly, you can store an approximation of P. So instead of using P, use Q, which is an approximation of P, but you can represent Q using small number of bits. Right? So perhaps you would want to quantize P and then use the quantized representation of P instead of P itself. So let's say if the quantized representation is Q, then then you design the code according to Q, even though you know that the actual distribution is P, and therefore uh, the expected length that you would now achieve would be h of P plus dpq. So this is the penalty that you would need to pay for quantizing P. or using some approximation of P. Right?
Sure, but
Yes.
we calculate the probability distribution of each and every file that we need to compress, right?
Sure.
So why can't we say this way that two different files may have completely different distributions
Mhm.
and may have come from the same source, which is English language or something. But
Sure.
uh, why can't we say for each file it is a different source, even though it is same, because they may have different distributions, and say that whatever distribution we calculate is exactly the true distribution, because we don't need the exact true distribution because there is no more data. So can't we just say that Q of X is P of X?
Uh, Not really. So okay. So again, uh, well, ultimately it depends, right? So you achieve and expect you achieve some length. So after all, what you are given is some realization, right? When you compress, you're using some realization of Excel. All right. So at each point, you're using a different uh, sequence. So, okay. So let's let's consider the following experiment. So you have, let's say you have multiple files. Okay. Uh, so you have file, say x n of 1, x n of 2, up to say xm, oh sorry, xn of m, right? All of these, let's say, are whatever English text files are. They're all identically distributed text files. Okay, and for each you use a different, you use the empirical frequency corresponding to that particular file and then compress it, right? Uh, Whereas the if you wanted to get an exact estimate of the true distribution, you would need to take the empirical frequency across all possible sequences put together, right? So the best possible uh, rate that you could achieve would be n times, sorry, m times h of xn, right? Which is m times summation xn. I put it this way. Oops. This would be m times n h of x, which would be m times n summation over all x p of x log 1 over p of x. So if you encoded them, if you sort of bunched all of them together and then compressed uh, the whole thing, all the m files together, then this would be what you could possibly achieve. Now, when you're encoding them separately, each of the empirical frequencies of each of these could be slightly different, right? Uh, so in fact, you use you have summation j going from 1 through m of n times summation over all x qj of x. Uh, yeah, so what you get qj of x log 1 over qj of x. Do you agree? So this is what you would get if you. So this is what you were. Yeah. So this is if you encode all the files jointly, and this is what you would get if you encoded the files separately.
Yes, sir, but now we are at a level where like we were initially talking about symbols and then the files, right? So if you want each file to be optimized, maybe assuming q of x equals q of x is better, right? Rather
Yeah.
than the
So
joint
so
of.
so, so that is what you would be doing here, right?
Yes, sir. But what I'm saying is we are assuming all of them were from the same source. But what if they were actually not? Like just because they were English text files does not mean they would be of given distribution, right? Two people can write completely different English text. Like
Correct. But then if you take a large enough English text file, then irrespective of who wrote it, you would still get the same empirical distribution.
yes, sir, but that would actually be averaging out and taking a different distribution than each file is, right? Suppose if
Okay.
our goal is to compress the file, not the
Uh-huh.
bunch of files to the maximum extent,
Mhm.
assuming q of x as p of x would be better.
So that is what we do, right? We always assume that q of x equal to p of x. But in fact, so the point that I'm trying to make is that choosing q of x equal to p of x and then designing it would in fact not be optimal, right? So if we chose q of x to be p of x, let us say that we do that, then this would be the rate that we would achieve. Do you agree with this point at least?
Yes, yes.
Yes, right? So, but then on the other hand, if you looked at sort of all the files put together, uh, summation j equal to 1 through m of qj of x. So qj of x is the empirical frequency for the jth file. Okay. But then the average would be, so this divided by m is in fact the sort of true distribution, which is p of x.
Yes, yes, sir.
Mhm.
I understand what you're saying, but
Okay.
what I'm saying is,
Yes.
if our goal is to minimize the rate of compression or the size of a single file, but not a bunch of files,
Correct.
wouldn't we actually be like evaluating it? Like, wouldn't we actually be getting the best possible compression on that with just empirical frequency?
Yeah. So if you're considering just a one-shot compression, then that is the best that you can possibly do. You can't do any better than that anyway, right?
Yeah. So like even with the empirical frequency, we're doing it the best possible.
Yeah, that is the best possible thing that you can possibly do. You cannot do anything better than choosing, say, the empirical frequency or some estimate because you don't have any more information, right? If you had extra information, you could of course use it, but you can only use the empirical estimate of what you have, correct?
Yes.
Right? But on the other hand, if you had this additional information that if you're doing the compression for m different files, m different IID files, then you can actually do better. I mean, of course, you cannot achieve this, right? Because you didn't have this extra information of what p is. But if somehow the genie knew gave you what p was, then you could in fact achieve a rate of uh, h of p. But now what you achieve is only h of p plus dpq.
Yes. But even if we knew p of x, like
Correct.
somehow,
Yes.
if we use p of x to encode a single file, that would
Correct.
actually be maybe larger than if we use q of x to encode it, right?
Correct. So potentially it could be larger. It could be larger for some files. It would be smaller for some files.
So it cannot be smaller, right?
Uh, so let me see. Uh, so if you used It could potentially be smaller. So let us say that we knew. So suppose that someone gave us p,
Yes.
okay, and we choose our sequences based on p. Okay, so let's say that. So we know p. We design the code according to p. All right. So we design it according to p, but then the empirical frequency for that particular file, for one file, turns out for the jth file is qj. Okay.
Yes.
Yes. So what is the expected length that we what is the length that we achieve for it for the jth file? It is summation qj of x log roughly log 1 over p of x. I'm ignoring the CL and stuff like that. All right.
Yes.
Right. So what is this equal to? This is h of q plus dqp. Right.
Yes.
You agree? Okay. So this is fine. But this in general could sometimes could be larger than h of p, but sometimes it will also be less than h of p. It's always greater than h of q. I agree with that. But ultimately overall the what we are aiming to achieve is h of p, not h of q.
Yes.
So for some files we'll do better than h of p. For some files we'll do worse than h of p. But on average we'll still be achieving h of p.
Thank you.
Right? But on the other hand, if instead of p, if I designed it according to q, then then on average I will do worse than h of p. It's always h of p plus dpq.
Yes. Thank you.
Okay, that's a good question. Any other questions?
Sir, for text files, we'll calculate empirical frequencies and all, but for when coming to audio files or image files or video files, so
Sure,
there
sure.
how we are gonna estimate this P of X?
So once again, it depends on what the values are. So typically, well, when you're talking about audio or video files, it is usually lossy compression. But although there is also a lossless compression component to it, so typically, if you have, let's say, an audio file or an image or whatever it is, what you first do is you quantize it. Uh, so in principle, so an audio file or let's say a voice signal would be a continuous time, continuous amplitude signal. But then you first sample it and then you quantize the number of levels so that you bring it down to some finite alphabet. Right? So ultimately, you still bring it down to the situation where your alphabet x, so you have an xn which is sampled and quantized, and this belongs to uh, some calligraphic x raised to the n, where this could be maybe it would have like 256 levels or maybe 1000 levels or whatever. So the alphabet size would be much larger, but still it's basically boils down to the same scenario.
Okay, okay, sir.
Right? And then you can do all of this. Ultimately, for each, so that is, yeah. So in this course, we are basically trying to design general purpose compressors. Right? We're using a mathematical framework to abstract out the problem. And if you didn't have any extra information about the source, then this is the best that you could possibly do. But on the other hand, if you're trying to design special purpose compressors, so for each application, you generally have some extra information about the source. So a text file, for example, is going to be different from an image file, and this is going to be different from a video file, and so on. Right? And in each case, you can always do more engineering optimization to get a better compressor. Right? So for example, even if you take, for example, zip, now, if you try to compress, you do this experiment yourself. So take different types of files and try to compress them using zip. So you'll see that for text files, you get very good compression. For image files, you get very good compression. But on the other hand, if you try to compress, say, an MP4 file, you will get very bad. You don't really get much compression at all, right? Because it's already been optimized and you can't improve this any further. So, so a special purpose compressor designed for that particular application will usually do much better than a general purpose compressor like Huffman codes or arithmetic codes or LMPLZIP or whatever we discuss in this particular course. But ultimately, whenever you're designing a special purpose compressor, they'll typically be using these algorithms as building blocks. So when you design zip or when you design JPEG algorithm or an MPEG algorithm, you will not be using just one of these algorithms. You'll be using a whole bunch of different techniques, out of which maybe the Huffman code is one component, maybe the arithmetic code is one component, maybe the Lempel-Ziv algorithm is one component. All right. So, any other questions? Okay, so maybe this is a good time to have a quiz. I've put up the link in the chat box. In case you're not able to access it, let me know. Yeah, so the link for the quiz is on the chat in the chat box.
Hello, sir. Hello.
Yes or no?
Sir, in the question, this it is given dyadic and non-dyadic. What is the use of that, sir? I think
That is something that you have to think about.
no, sir. Actually, yeah, I know, but nothing is there the equal to or like that. It it is for the general. In both the questions, it is for general sequence like Hoffman, Shannon.
It doesn't matter. So I'm talking about the distribution, right? So a dyadic distribution is one where all the probabilities are 1 by 2 raised to some integer, right? So how you use it is up to you.
Okay, sir.
Yeah, so you just have to say whether each, so for Anurag's question, it's, yeah, so if something is equal to, if x is equal to y, then certainly x is less than or equal to y, right? Okay, so you can take, maybe take 1 more minute. No, there are no typos.
Sir, can I ask question about the assignment?
Let's finish this perhaps.
Okay, sir.
Okay, so anyone left to fill the quiz? Anyone who hasn't submitted the quiz yet? Okay, so let's stop accepting responses. Okay, so before I come to your question, Anu, let's very quickly go through the quiz questions. So the first question was, consider a non-dyadic distribution Px with, just one sec. Right. Share. Right. So you're given non-dyadic distribution Px where the entropy is whatever 2.3 bits. Right, and the first question is symbol-wise Huffman encoding achieves Huffman achieves a rate, an expected length of less than or equal to h of 2.3 n plus 1 bits. So LH of xn is less than or equal to 2.3 n plus 1 bits. Is this true? No, this is not true, right? Because it cannot be achieved for all n. So uh, if the sequence is non-dyadic, then the Huffman code always achieves, so LH of x is strictly greater than h of x, right? So it's equal to h of x plus some alpha for some alpha which is strictly greater than 0. So if you do symbol-wise encoding using Huffman codes, then you achieve an expected length of n times h of x plus n alpha. So this quantity grows as n tends to infinity. So the expected length that you can achieve is for large n is going to be much larger than 2.3 n plus 1 bits. So this statement is false. The second statement is arithmetic encoding of xn achieves expected length of less than or equal to 2.3 n plus 2 bits. This is of course true. Symbol-wise Shannon-Fano-Elias encoding achieves an expected length of less than or equal to 2.5 n bits, which is false because uh, h of x is 2.3 bits, and we know that the Shannon-Fano-Elias code achieves an expected length of great at least h of x plus 1 bits, which is 3.3 bits, which is strictly greater than 2.5 n bits. So for large n, it's going to be greater than this. So the two statements which are false are symbol-wise Huffman encoding achieves expected length less than or equal to 2.3 n plus 1 bits. That is false. And symbol-wise Shannon-Fano-Elias encoding achieves expected length less than or equal to 2.5 n bits for all n. So these two statements are false. For the second case, so here in the first problem, the main idea was that for Huffman codes or any code for that matter, the expected length that you can achieve is strictly larger than h of x bits. So the expected length is strictly greater than h of x if the source is non-dyadic. So you can achieve uh, an expected length of so so the expected length can be equal to the entropy only if the source is dyadic. All right, and this is something that we've seen in the previous two classes. So for the second uh, question, consider a dyadic distribution with entropy 1.5 bits. The first statement was symbol-wise Huffman encoding achieves expected length less than or equal to 1.5 n bits. So 1.5 n is in fact n times the entropy of the source. And for a dyadic distribution, Huffman codes achieves entropy. So the first statement is true. Arithmetic encoding achieves expected length less than or equal to 1.5 n plus 2 bits. This is also true. This is the standard arithmetic coding which we saw in the last class. Then symbol-wise Shannon-Fano-Elias encoding achieves an expected length less than or equal to 2.5 n bits for all n. So for dyadic distributions, uh, log CL of log 1 over p of x plus 1 is equal to log 1 over p of x plus 1. So the expected length achieved by the Shannon-Fano-Elias code would be n times h of x plus 1. Shannon-Fano-Elias is always equal to h of x plus 1. So for symbol-wise encoding of n symbols, this is n times h of x plus 1. So the third statement is correct. But the symbol-wise Shannon code, so symbol-wise Shannon encoding achieves an expected length of h of x times n. So the last statement is incorrect. All right. Uh, so when we say that LH of x, so let's say LH of x1, so this is h of x plus alpha. Alpha is less than 1, that's fine. But alpha is strictly greater than 0, and that is all that I care about. Because when we do symbol-wise encoding, of xn, the expected length is equal to n times the expected length over here. So it is n times h of x plus alpha. So this is n h of x plus n alpha. For some alpha which could be small, doesn't matter. It could be, so alpha is between 0, strictly greater than 0, but it could be less than or equal to 1. But for large enough n, this is going to be greater than n h of x plus 1 for large n, in fact for any n greater than 1 over alpha. Right? Alpha cannot be greater than 1 because we know that the Huffman code achieves an expected length less than or equal to h of x plus 1 bits. Right? So symbol-wise Shannon-Fano-Elias code achieves. So, sorry, what is the question? So right, so that was a point, right? So if we have a dyadic source, right? So if it's a dyadic source, then what does the Shannon-Fano alias encoding do? It assigns code word length of log CL of log 1 over px plus 1 bits, right? So this is, since the source is dyadic, CL of, so log 1 over p of x is an integer. So this will be equal to log 1 over p of x plus 1 if p is dyadic, and therefore, so this is k of x for Shannon-Fano alias. So the expected length is basically equal to entropy plus 1 bits, which is 2.5 bits, right? So for symbol-wise encoding of n symbols, you achieve an expected length of 2.5 n bits, right? So in question 1, sorry, so you're talking about for the non-dyadic question. Let me go back. Shannon-Fano alias. Oh, okay. So that is indeed false. That is not true. So for the non-dyadic question, symbol-wise Shannon-Fano alias encoding will achieve an expected length greater than that. Yeah, so that statement is false, right? Because if you wait, okay, symbol-wise Shannon encoding achieves expected length less than or equal to 3.5 n bits for non-dyadic. Yep. So what does the Shannon encoding do? Yeah. So the Shannon encoding achieves, for each symbol, the expected length is less than or equal to h of x plus 1 bits, which is what, 2.3 plus 1, 3.3, which is strictly less than or equal to 3.5, right? So if you do symbol-wise encoding, the expected length is always less than or equal to n times 3.5 bits. So Shantanu, what you have put in the chat box is always true, right? So so those statements are correct, but the question is, for what distributions does equality hold? So LH and LS achieve an expected length of n times h of x if and only if x is dyadic. All right. If it is non-dyadic, then the expected length is strictly greater than h of x. And so, okay. So, so for dyadic, LH is always equal to, so LH, if you do symbol-wise encoding, then LH symbol-wise of xn is always equal to n times h of x. Shannon symbol-wise of xn is equal to n times h of x. Shannon-Fano-Elias symbol wise xn is equal to n times h of x plus 1 bits. For non-dyadic, LH symbol wise of xn is strictly greater than n times h of x. In fact, it grows linearly with n. So this is n times h of x plus alpha for some alpha greater than 0. L Shannon symbol wise is equal to n times h of x plus maybe some beta, where again beta is greater than 0 but less than 1. And Shannon-Fano-Elias symbol wise of xn is n times h of x plus 1 plus gamma for some gamma greater than 0 but potentially less than or equal to 1. So for dyadic, the minimum Huffman, yeah. So for dyadic sequences, the Huffman codes achieves an expected length equal to 1.5 n bits, right? As I said, if it is equal to 1.5 n, it is obviously less than or equal to 1.5 n bits. It's equal to, yeah. But if a equal to b, then this statement is also true that a is less than or equal to b, right? So a equal to b implies that a is less than or equal to b. Uh, right? It's written that it is less than or equal to.
Sir,
Yes?
sir, if it is equal to 1.5, so
Yes.
how do we can means it is equal to all for all n. So how do we generalize that it is less than or equal to 1.5 n? Means
So that's
by
what I
seeing
said,
the
right?
state,
If a equal to b, then a is obviously less than or equal to b, right?
sir, less than not holds right.
Yeah, it is not strictly less than. I never said that, right? It is less than or equal to. So 10 is
Yes.
less than or equal to 10. It is not less. So I can't say that 10 is less than 10. 10 is equal to 10, of course, but 10 is obviously less than or equal to 10.
So I was finding this equal to everywhere because means this we can't say like yeah 10 is less than or equal to 10, but when it is always equal to 1.5, we know that for dyadic it is equal to that. So why it is written like that? It was confusing, sir.
Sure, it's designed to make you think more, right, on your feet.
Okay, sir.
Sir, are these bounds just now explained, are these valid
Huh?
for IID sources or for any type of sources?
Yeah, so these are only for IID sources. Well, okay. So these statements are true for sorry. So these are true for all stationary sources, not necessarily IID. This is the expected length that you can achieve if you do symbol-wise encoding.
Okay, okay, sir.
Okay. So any other questions?
So, sir, in yesterday's question regarding these bounds, so in every statement it is written for every source. So then obviously those statements will not be valid for every source, right?
Sorry, which question?
In yesterday's quiz question,
I guess there was no quiz. Yes.
I mean, I'll just post it
Sorry,
here.
sorry. Yeah, yeah. Sorry, my bad. So there was a question. I don't remember what the question was.
I'm posting the statements.
So okay, so there were okay. So for every source with a dyadic PMF, the Shannon code achieves an expected length of h of x. Is that- Yes. So this was for n equal to 1, right? So all of these statements are for n equal to 1.
Okay. Okay. For n equal to one, I mean, source cannot be. I mean, the source cannot be with memory or something else.
Yeah, it doesn't make sense, right? It's just one single symbol.
Okay.
So that's the difference between encoding a single symbol, which is really what we've discussed for most part of the course, versus encoding an entire block of symbols.
Okay. Okay.
So any other questions? Okay, so let's end the meeting for today.